In this video, we would be looking into clustering and some different types of clusterings along with their algorithms. So clustering is an important concept when it comes to unsupervised learning. It mainly deals with finding a structure or pattern in a collection of uncategorized data. Clustering is the task of dividing the population or data points into a number of groups such that the data points in the same group are more similar to other data points in the same group than those in other groups. In simple words, the aim is to segregate groups with similar traits and assign them into clusters. You can also modify how many clusters your algorithms should identify. It allows you to adjust the granularity of these groups. There are different types of clustering. We have hierarchical clustering, k-means clustering, KNN, which is the k nearest neighbors, then principal component analysis, singular value decomposition, and independent component analysis. So in this video, we would be going into depth with the k-means clustering and PCA. PCA, which is the principal component analysis, is a statistical procedure that allows you to summarize the information content in large data tables with the means of a smaller set of summary indices, also called as principal components, that can be more easily visualized and analyzed. The most important use of PCA is to represent a multivariate, which is multivariable, data table as a smaller set of variables in order to observe trends, jumps, clusters, and outliers. In short, PCA is used for dimensionality reduction. Dimensionality can be further classified into feature extraction and reduction. Now what are they? It is exactly what their name suggests. And I hope if you watched the last session, you would remember that feature reduction was used to prevent overfitting. But here the question arises, where do I use PCA? If you want to remove your variables but you can't identify which ones to remove, if you want to make sure your variables are independent of each other, and if you're comfortable with making your independent variables less interpretable, that's when you use PCA. If you answered no to point 3, then you should not use PCA. So now let's look into the PCA algorithm to better understand how we can make these principal components. So in step 1, let's consider a matrix X with n rows, aka the observations, and k columns, aka variables. For this matrix, we construct a variable space with as many dimensions as there are variables. Each variable represents one coordinate axis. For each variable, the length has been standardized normally by scaling to unit variance. In step 2, each observation, which is the row of the matrix, is placed in the k-dimensional variable space. Consequently, the rows in the data table form a swarm of points in this space. Now in step 3, this is the mean centering stage. In the mean centering procedure, you first compute the variable averages. This vector of averages is interpretable as a point, which is the red dot in the space. The point is situated in the middle of the point swarm, which is the center of gravity. In the mean centering procedure, it corresponds to moving the origin of the coordinate system to coincide with the average point, here in the red. And now, the data set is ready for computation of the first summary index. The first principal component, which is PC1, is the line that best accounts for the shape of the point swarm. It represents the maximum variance direction in the data. Each observation, which is the yellow dot, may be projected onto this line in order to get a coordinate value along the PC line, and this value is known as a score. You can do the same thing, you can follow the same algorithm to find PC1, PC2, PC3 and so on to better understand where there's the second best variance of the data, third best variance of the data, and so on. The next clustering we're looking into is k-means clustering. K-means is an iterative clustering algorithm which helps you to find the highest value for every iteration. Initially, the desired number of clusters are selected. In this clustering method, you need to cluster the data points into k groups. A larger k means smaller groups with more granularity. And in the same way, a lower k means larger groups with less granularity. The output of the algorithm is a group of labels. It assigns data points to one of the k groups. In k-means clustering, each group is defined by creating a centroid for each group. The centroids are like the heart of the cluster, which captures the points closest to them and then adds them to the cluster. Let's look at the k-means algorithm now. The way k-means algorithm works is as follows. So you specify the number of clusters k, initialize the centroids by first shuffling the dataset and then randomly selecting k data points for the centroids without replacement. Keep iterating until there is no change to the centroids. That is, assignment of data points to clusters isn't changing. Compute the sum or squared distance between data points and all centroids. Assign each data point to the closest cluster, also known as the centroid. Compute the centroids for the clusters by taking the average of all data points that belong to each cluster. Now that's quite a lot of details to take in, but I think it would be better explained when shown with visuals. So let's look in step 1. We specify the desired number of clusters k. So we choose k is equal to 2 for these 5 data points in 2D space. In step 2, we randomly assign each data point to a cluster. So here we assign the 3 points in cluster 1 shown using the red color and 2 points in cluster 2 shown using gray color. In step 3, we compute the cluster centroids. The centroids of data points is the red cluster. In the red cluster is shown using red cross, and those in the gray cluster is shown using a gray cross. We reassign each point to the closest cluster centroid. We note that only the data point at the bottom is assigned to the red cluster even though it's closer to the centroid of gray cluster. Thus, we assign that data point into the gray cluster. So in step 5, we recompute cluster centroids. Now recomputing the centroids, so we will be recomputing the centroids for the clusters. And in step 6, we repeat steps 4 and 5 until there are no improvements possible. We keep doing this until we don't, until we reach a global optima. When there will be no further switching of data points between two clusters for 2 successive repeats, it will mark the termination of the algorithm if not explicitly mentioned. Okay, now let's use k-means into some practical use. Here we'll use k-means to compress an image. The image that we'll be working on is 396 into 396 into 3. Therefore, for each pixel location, we would have 3 8-bit integers that specify red, green, and blue intensity values. Our goal is to reduce the number of colors to 30 and represent or compress the photo using only those 30 colors. To pick which colors to use, we'll use k-means algorithm on the image and treat every pixel as a data point. That means reshape the image from height x, width x channels to x channels. So we do height into width x channels. That is, we would have 396 into 396, which is 156, 816 data points in 3-dimensional space, which are the intensities of red, green, blue. So doing so will allow us to represent the image using the 30 centroids for each pixel and would significantly reduce the size of the image by a factor of 6. The original image size was 396 into 396 into 24, which is these many amount of bits. And now the new compressed image would be 30 into 24 plus 396 into 396 into 4, which is 627,984 bits. The huge difference comes from the fact that we'll be using centroids as a lookup for pixels color, and that would reduce the size of each pixel location to a 4-bit instead of an 8-bit. So what are the applications of unsupervised learning? Some applications of unsupervised learning techniques are as follows. So clustering automatically splits the dataset into groups based on their similarities. So anomaly detection can discover unusual data points in our data set, and it is useful for finding fraudulent transactions. Association mining identifies sets of items which often occur together in your dataset. So latent variable models are widely used for data pre-processing, like reducing the number of features in a dataset or decomposing the dataset into multiple components. We would now end the lecture section of the workshop series by looking into the disadvantages of unsupervised learning. So, like with all the information, with everything that you have heard me talk about, you would have realized that you cannot get precise information regarding the data sorting and the output as data using unsupervised learning as it is unlabeled. We get less precise information, which implies that there's low accuracy of the results due to unlabeled data. And lastly, the user needs to spend a lot of time interpreting and labeling the classes which follow that classification. So these are some of the disadvantages of unsupervised learning, but there are also various advantages of unsupervised learning, which we had talked about in the slides previously. So now our next video would be a tutorial section wherein you would learn how to use k-means compression on an image. Thank you.